Give it a sec, it's still going. And we are on.
Can I start now? Hello, everyone. Welcome to the first ever virtual technical tours. I'm Anam, and I'm the technical tour manager for this year's conference. And with great pleasure, I'll be your host for this session today. So we have two very exciting projects by Q-Free and Stantec. For the first part of the hour, we're going to take you on a video tour of an area in Snohomish County with an adaptive signal control system presented by Q-Free. Next, we're going to show you a video tour of a real-time traffic monitoring system for a 700-kilometer corridor in British Columbia presented by Stantec. We're also going to have a live Q&A with our presenters for each of the technical tours, so please submit your questions in the Q&A tab. So with that, I'd like to introduce the presenters for our first technical tour. We have Steve Mager and Patrick Marnell from Q-Free. So Steve Mager is responsible for the sales of Q-Free's traffic management products and services throughout the Western US and Canada, to include Hawaii and Alaska. Steve has worked in the ITS arena for over 10 years with a focus on adaptive traffic systems, connected vehicles, and central and local traffic control systems. Patrick Marnell is a senior project manager at Q-Free and specializes in helping people build and deploy advanced traffic signal systems. Additionally, he works with a talented team of software engineers to drive development of traffic signal system software that provides innovative solutions to meet the needs of agencies across North America and the world. Prior to joining Q-Free, Patrick was a consulting engineer. He's currently the Western District ITE Technical Chair and member of the Oregon Traffic Control Device Committee. Patrick has a bachelor's and master's degree from the Oregon State University. So we're pleased to have Steve and Patrick here with us today. So I wanted to give just a brief description about the project before we get into the video. So Q-Free currently has an adaptive traffic signal control system that operates along 6 major corridors within Snohomish County at 49 signalized intersections. Q-Free envisions that this will optimize traffic flow and improve safety on the corridors. This adaptive system utilizes industry-leading algorithms implemented locally at the intersections. Since Snohomish County does not have a standard traffic control management center, this allows for a mobile TMC. Q-Free plans to expand the selective adaptive signal system beyond this initial deployment in Snohomish County to include an additional 32 intersections. So with that, let's watch the video to learn more about this project. Any questions that you may have for our presenters as you watch this video, please feel free to drop in the Q&A tab, and they'll definitely answer them in the Q&A session right after. So let's watch the video now.
This is an AM travel time run on US 96 in Snohomish County, Washington. This corridor was configured to heavily favor progression towards I-5 in the AM peak period. During the PM peak period, the corridor is configured for progression in the opposite direction. Adaptive also allows us to program stops within the corridor. This intersection is programmed with an allowed stop in MaxTime Adaptive so that we can build a platoon. Then we can make sure the platoon makes it through the next set of intersections without stopping. This is an AM peak period corridor plan which favors the left turn movement onto I-5. The goal is to flush as many cars onto the freeway as possible to facilitate heavy commuter traffic. However, on the rest of the corridor, we continue to favor the westbound direction. The intersection we're looking at now is a crossing corridor, where we have two adaptive corridors crossing each other. Adaptive also allows for advanced features such as flashing yellow arrows. You can use flashing yellow arrows for protective permissive operations by time of day or by condition, which is what we're doing on this corridor. No additional programming is needed within MaxTime Adaptive to run advanced features. All the advanced features are pulled from existing patterns and programs that are running in MaxTime and will continue to run during adaptive operations.
Okay, so now we're going to jump into the Q&A session. So if there are no questions in the chat, I guess I'd like to ask a few questions. So thank you, Steve and Patrick, for joining me today. So I'd like to ask you a few questions. So what are some of the challenges of working across multiple agencies to create such a seamless adaptive control system?
Sure, excuse me, I'll take that one. So this project was really multi-jurisdictional. We had 5 different jurisdictions which own signals on the corridor, and then 2 IT networks. So we were dealing with the Washington Department of Transportation IT network and then the Snohomish County network. You know, the challenges are typically focused around communication. You just need to get everyone talking the same language and get the right people in the room to solve those problems. So for just one example, our adaptive system, MaxTime Adaptive, requires the intersections to talk locally to each other, but doesn't necessarily require a central connection between the intersections. So we were able to coordinate with the Washington DOT and Snohomish County IT departments, and we put them on a call with one of our IT folks, and basically they hashed out a plan that would let the Snohomish County intersections exist on the WSDOT network using something called NAT IP addresses. That's network access translation, if I recall correctly. So essentially, those devices showed up on WSDOT's more secure network, which let all the intersections talk to each other, and let us implement our solution here. So it's no secret. It's just getting the right people talking to each other and doing that with enough time that people can get comfortable with the solution.
Okay, thank you. So we have a question in the chat. Is there an optimal spacing of the traffic signals for your system to work effectively?
Our system relies heavily on something called link pivot optimization. It's an algorithm that came out of some of the work from Purdue University, and really the concept of automated traffic signal performance measures that was pioneered by Purdue and also Utah DOT. Optimal spacing is no different than your normal signal timing. I like to have evenly spaced quarter-mile intersections, but the amount of times I ever get that is almost none. So I don't think we're ever going to be in a place where we get to plan our intersections spacing the way we want it. Best we can do is come up with a system that does a really nice job at working with what you've got. And that's why I'm excited about this link pivot methodology. It's essentially using the high resolution data that is generated by the traffic signal controllers. So we're getting an individual detector hit that is recorded on your advanced detection, whether that's loops or radar zones or video, whatever that is, we're getting that blip coming into the system, and that is used to determine whether or not your vehicles are arriving on green or arriving on red at the intersection. And then the key of that link pivot algorithm is just a programmatic way of optimizing those arrivals on green across the corridor.
Okay. So what type of communication is being used to allow controllers to communicate locally? Can you comment on how much maintenance is required to the adaptive parameters to ensure the system operates optimally?
Yeah, so as far as communications, we need a local connection between controllers. So each controller on an adaptive network needs to be able to talk to the other controllers on that adaptive network. I think you mentioned before we had 49 intersections as part of this deployment, but we broke that into 6 sub-corridors. So those intersections only have to talk to, 6 to maybe 15 intersections, however they're broken up there. If we do lose communications to an intersection, the system is smart enough to look at where that break exists and say, aha, I can run this as 2 kind of separate sub-adaptive networks while that communications is out. And then when communications is restored, the system links back up and starts working as a whole system. There's a little asterisk there, and that's we allow a setting to say this intersection is a critical intersection. If I lose communications to this intersection, it's not worth running the adaptive system, and then the whole kind of adaptive network will drop back to its regular time of day schedule. When it comes to maintaining an adaptive system, I like to, I really feel like our system evolves over time. So when we configure an adaptive network, we absolutely go out in the field. We like to spend about a week out on the corridor, fine-tuning it, and then follow up with a second week of remote observations. And what happens during that time is we're setting up these condition plans. And essentially those conditions will look at a detector or a set of detectors or a phase, and it can look at volumes or occupancy or a bunch of different parameters. And we build these condition plans based on those actual observations of what's going out on your corridor. And then we have it take specific actions. So over time, as you maintain a system, you'll naturally add more of these condition plans. You'll see an unexpected event on your corridor, maybe a big traffic accident on a parallel corridor shuts down a route, and you get an influx of volume. And you'll say, well, I didn't exactly like how the system handled that, so I'm going to add this condition to the plan to better accommodate that. So over time, you really evolve this to a better and better functioning adaptive system.
Okay. So what kinds of detection, main street, link, entry, stop line, side street, does the adaptive system solution require?
Gotcha. So the adaptive detection requirements are based around the detection requirements for automated traffic signal performance measures. We do that because we rely on some of those methodologies, and also we feel like it's a good choice. You get a lot of value out of that detection layout, because you're also going to get things like those ATSPM charts from our central max view system. The quick summary of what detection is needed is we want stop bar detection, lane by lane stop bar detection all the way around the intersection. And then we want advanced detection, preferably lane by lane, but we can work with approach detection for the advanced. And we need that on your coordinated movements. So typically your mainline movements, we need that advanced detection. When it comes to actual detection technologies, whether it's loops or radar or video, we're pretty agnostic. We rely on individual jurisdictions to tell us what they think the best detection system for their network, for their specific conditions are. And we can really work with whatever you think is going to give us the highest quality data inputs.
Okay. So how do you see connected vehicles being integrated into your system in the future?
Sorry, I didn't quite catch that.
So how do you see connected vehicles being integrated into your system in the future? So how would they work with autonomous vehicles?
That's a really good question. Q-Free does make a connected vehicle application, actually a couple connected vehicle applications. We have a locally installed connected vehicle application, which gets installed on the controller in the field. And it can manage the broadcast of SPAT and map data over DSRC or 5G. To be honest with you, the current connected vehicle applications are just kind of following the lead of the controller, the adaptive software. So that application would broadcast information based on the choices that the adaptive or local software make, and it would provide that information to drivers. But you know, the industry really just isn't quite there.
Yeah.
The point where we'd actually be taking information in from connected vehicles and using that to make better decisions. I hope we'll get there one day. I believe we will, but
Right now, every connected vehicle one is just one way. It's from the ATMS out to companies like TTS or app companies like CV. But at this point, none of these companies are sharing data back with the agencies. So until that point happens, you're not going to see a lot of interaction on like an adaptive system with it.
So can your system accommodate transit signal priority?
Absolutely. Actually, we have TSP programmed at 6 intersections on the corridor. It's not running currently. The jurisdiction is in the process of procuring their TSP detection, so the phase selectors for their TSP system. In general, all of the advanced features that exist within the max time intersection controller software are available for use during adaptive. How the adaptive system works is both max time intersection controller and max time adaptive are installed on the same processor. Max time intersection controller, just our standard local controller, is always in control of your intersection. It passes data from the detectors to the adaptive program, which comes up with adaptively generated cycle split and offset combinations. And then max time adaptive passes that information back to the local controller, which implements it. So as far as the actual intersection is going, it doesn't know that it's running adaptive. It just thinks it's got someone plugging in a new cycle split offset combination every couple minutes.
Okay, and that's all the time we had for our Q&A. So thank you so much, Patrick and Steve, for being here with us today. And I think we have Stantec up next.
Hi, Anna.
Hi.
Hi, Anna.
Hi, Cynthia. So
Nice to
up
meet you.
next, nice to meet you as well. So up next, we have our second technical tour by Stantec. I'd like to introduce you to Samit and Cynthia. So Samit has more than 20 years of experience on a variety of transportation engineering and planning projects. His experience includes transportation planning, pedestrian and transit analyses, vehicular traffic capacity analyses, and has specialized skills in planning for major events. Samit is currently working with dozens of clients to develop data analytics solutions. He's helping them combine data from dozens of multiple historical and real-time data sources to extract meaningful insights, develop operational recommendations, and predict changes in operational strategies using the latest frameworks in machine learning and deep learning industries. He's leveraging these tools to help develop solutions that improve mobility, design, operations, and safety. So now I'd like to introduce Cynthia. Cynthia Albright has planned and designed award-winning transportation projects, presented, authored, and served as an advisor to clients, community groups, professional peers for 35 years. She is one of 53 certified urban designers in the US. Her primary focus and passion are on digital change, strategy development, project delivery, and ensuring the use of the most intelligent data tools, dynamic dashboards to effectuate positive change. As a geographic information systems professional, Cynthia brings her expertise with numerous data sources and types coupled with geospatial analytics to drive smart transportation investments, asset management, and traffic modeling. As a fellow in the American Institute of Certified Planners, she's hyper aware of new technologies across multiple business sectors, which allows her to bring innovation to projects that help agencies create livable, equitable, and sustainable environments that integrate equity and climate change principles. So a little bit about the project before we watch the video. Stantec has implemented a real-time traffic monitoring system for a 700-kilometer corridor between Edmonton and Vancouver in response to the challenges with standard traffic monitoring methods in the region. So this tour will present video drive-throughs of the project area and discuss the details of how the real-time analytics for the 700-kilometer corridor were developed, as well as the numerous measurement strategies utilized and the types of data that was collected to enable the identification of high traffic areas and view congestion in real time along the corridor will also be presented. Furthermore, this tour will show how this data was used to prolong the onset of congestion in real time in the field by effectively identifying external factors that contribute to congestion. So just a reminder to please submit any questions that you may have for our presenters in the Q&A tab, and we'll get to them after the video. Okay, so let's watch the video now.
Trans Mountain Expansion Pipeline Project with Stantec Consulting. Trans Mountain hired Stantec Hello, everybody. My name is Cynthia Albright, and I'm coming to you from Reno, Nevada. I'm a member of the Trans Mountain Expansion Pipeline Project with Stantec Consulting. Trans Mountain hired Stantec to help them develop an approach for monitoring traffic congestion along a 750-kilometer corridor between Jasper and Vancouver. The provinces of Alberta and British Columbia allowed the contractors, of which there are 7 of them, no more than a 20-minute travel delay as a result of construction at any point in any one of the 2 provinces. Because the corridor is so long, has such an amazing amount of topography and wildlife, and of course, communities that access the corridor, we were hired specifically to develop a really unique approach that would allow the contractors to know in real time whether or not they were approaching that 20-minute time period. And of course, the provinces and Trans Mountain to know whether or not the construction delay was exceeding or even approaching that 20-minute time period.
We approached the problem by thinking about what the solutions were. We knew that we needed some kind of online data sources, and we evaluated several data sources from Google Maps to Here Maps to Waze. We looked at streetlight data to set a historical baseline. I'm talking about adjusting for seasonality. And we compared all of these sources to actual field runs. So to make sure that we were reporting data that was accurate, we actually had staff that went into the field and conducted runs between Kamloops and Jasper and Kamloops and Vancouver several times. And we were able to take their data, their actual speed observations from the field, recorded at every second, and compare that to each of these sources. So we created a matrix, and we said, which of these is the most reliable sources? And we found out that we really have to use an ensemble of methods. It wasn't just that there was one data source that was really much better than all the others. We had to combine different sources together to get to the real truth of the level of travel activity and the level of delay in specific sections of the corridor. The key to this was monitoring traffic in real time and also displaying it and conveying the information to the client in real time. So what we did is we developed an online dashboard that's still available, you can still look at, and that dashboard allowed them to look at what the traffic conditions were today, but it also put that traffic condition in context. So for example, today it takes you 2 hours to go between these 2 endpoints in the corridor. How does that relate to how it's been in the past? They were able to go back and look at the entire previous 6 months and say, the longest travel time we've had in this section of the corridor is, let's say, 2.5 hours. So having a 2-hour travel time is really not that bad. And we were able to adjust for that for things like weather that we talked about, for things like incidents, using all these sources. What we did before each morning is we had a list of where the construction zones were, and we were able to predict for each of the 100 segments throughout the corridor what the travel time should be. We wanted to enhance the transparency of the platform, and the reason for that was we wanted to give the client the information that we got as soon as we got it. It's about the real-time access and about the trust. What we're doing is we're telling you on Tuesday, this is what we observed. Yes, there was congestion, but we don't think it's caused by us. So when you get the phone call in 2 weeks, you have our logs that say, yeah, Tuesday at 3 p.m. there was a problem, but it wasn't because of construction. It was because we notified it. We noticed that there was congestion in the corridor, and we went ahead and did some observations, and it was because there was a wildlife crossing.
We couldn't use traditional situations of like having data nodes or like detectors on that entire section of that particular corridor. So what we did was we used different tools for creating virtual beacons at this particular points and using particular APIs to extract travel time information from each of these unique nodes on the entire stretch of the corridor. And all this data that gets captured every hour, we pull that in and we process and summarize that based on like Python-based coding to develop filtered summaries. And these all summaries become like separate data sets. And when these data sets get tied to the front end, which is just a visualization of these numbers into graphs or something like a chart or like geospatial mapping that the user can easily interact with. And when the user interacts with this data, the data sets in the background are recustomized based on the filters that the user is putting in. We also have a unique feature of identifying if a particular delay is caused by the construction activity or any arbitrary, based on, like, again, the algorithms that we built in. We are doing all that processing of removing any outliers on the back end so that it saves user time so that they can focus more on what the results and the trends are. And the dashboard is personalized for the client's need. So the information that we're providing them is for their question, basically, of like, how is the corridor functioning? Where is the delay happening, and by how much is it happening? And based on that, they can decide what strategy they can use for like alleviating that particular congestion in that point and making sure that the users, the end users of that particular corridor are not facing any detrimental, delays based on like the construction activity that's happening. In the future, we will also want to put like machine learning so that the particular product can actually give them recommendations based on what it sees in that particular section, that these could be the best recommendations, and that further gives the user more choices on like what they decide, and maybe have more of a control on like what they want to actually mitigate on, and have more time of maybe improving the process in general.
This tool that we've developed has numerous applications. Obviously, you can use it for construction monitoring on a project of this scale in an area of this type, going through the Rocky Mountains. But you can also use it to do construction monitoring for any project anywhere. We've applied the same tool to do incident identification. We can also use this to measure the benefits of new projects. If a new roadway opens up, or if there's a construction activity that ends, for example, what are the benefits of that? So we can look at the travel times, how many people are shifting from other roads, how much faster are those other roads as a result of this project. And another very useful application is predictive congestion. Because we're capturing real-time information and we're building a historical database, we know that on a Saturday in June, this is what the level of traffic should be like, this is how much congestion there should be. So we can use that to predict what's going to happen in the future. And there are steps that you can take to counteract that congestion if you know in advance when and where it's going to happen.
This was a huge benefit to Trans Mountain, and of course to the provinces of British Columbia and Alberta, because we're monitoring traffic in real time, but we can manage incidents in real time. Transportation agencies can collect data in real time from social media so that they know when these incidents are taking place and where they're taking place. And by using this kind of information, it allows all of us to know and to feel safer, because the transportation agencies are able to respond more quickly and to develop programs and roadways that are safer as a result of using information. Most importantly, no longer are we absolutely in need of making reports or printing emails or having emails, because this type of data can be processed on a dashboard, which makes it very, very easy. So we can all, thankfully, we can save a tree. And at the end of the day, I want to just thank you for being here. I want to thank you for listening to us. And I hope you enjoyed this presentation. Thank you.
Okay, so we're going to jump into the Q&A session. Thank you, Cynthia and Samit, for joining us today. So I'm going to see if, so we don't have any questions in the chat, so I'll just ask a few questions. So what were some of the difficulties with standard traffic monitoring methods in this region?
Some of the challenges with monitoring traffic in this region is because it's such a long region, 700 kilometers. You can't go out there and put sensors in the field to, if you have Bluetooth sensors or license plate sensors to be able to detect travel speed between different segments. We also looked at the difficulties in, we obviously can't have people doing travel time runs because you'd have someone or multiple people dedicated full time to doing travel time runs in both directions. And the challenge with that was because of the nature of the corridor and the remote locations, there were a number of cell phone dead zones in the corridor that extended in some cases 50 or 100 kilometers. So even if you had sensors, and even if you found a way to run them off of solar or have somebody go out there and replace the batteries, you still wouldn't be able to get that information in real time. And telling somebody, 6 hours after you've seen congestion that you saw congestion 6 hours ago just wasn't what the intent was. The goal was to identify that congestion in real time.
Okay. So how effective is this real-time traffic monitoring program? So do you have any data to show that it's effective, like maybe before and after studies?
Yes. So we have several studies that we've done. When we evaluate all of these different sources, we compare them to field runs that we've collected, and we cross-reference them to incident reports and to other data sources. So, we have people, for example, observing and doing video analytics on traffic cameras and looking at what the average travel speed is. And then we compare that to Google and to Waze and Here Maps and the other sources in real time. And now we're even looking at Rego. We develop a model to determine how good that fit is. And generally speaking, when we've used these to identify incidents in the field in real time for some of our communities, it's been pretty good at that. Whenever we identify that there is an anomalous traffic condition, it's usually been a very reliable indicator of an actual incident in the field.
And I would love to add that, particularly with the Trans Mountain Pipeline project, the fact that our dashboard enabled us to inform the contractors and we didn't have an incident whereby there was congestion that was even approaching the overall 20-minute travel delay was a successful outcome for purposes of our project, that we didn't have an incident that we had to have a contractor respond to in a way that couldn't accommodate the demands and the agreements by the contractor for the travel delay times.
Okay. So there's a question in the chat. Were there any blind spots along this long corridor where real-time data was not available?
That's a great question. We did have concerns about that, and that's why we calibrated the data to actual travel time runs. And what we found is that there really weren't any blind spots. When we saw congestion in each of these 100 segments on our travel time runs, it was being reported in the same way in the data in some way. So I think the way that it works on the back end is that these analytics sources, when they're recording your information in real time, so even if you're not in the field, even if you're not at that location, the next time that you do enter a cell phone region and you're able to ping, I think they impute what your travel time must have been in between. So if there's congestion happening in a certain location, when that vehicle approaches a location where they do have cell phone connectivity, then they impute from the time it took to pass through that dead zone what the travel time must have been inside that area.
Yes, that's correct.
So you mentioned you couldn't find a single source of data and needed to blend multiple sources to get an accurate picture. Can you explain a bit more about how that data fusion process works?
Well, I would say that one of the data sources that we used was location-based services data from Streetlight. And so we set a historical benchmark by analyzing a year's worth of data from Streetlight for the entire corridor to establish the travel times between these various nodes, volumes and travel times and travel speeds. And then I'll let Sumit speak about the real-time data, but we integrated data from multiple sources in order to not only just the travel times from the staff that were out in the field, but historical data using location-based services information, and then Google data that we purchased in advance so that Sumit could monitor that information for several months prior to the actual construction time period. But I'll let him speak to that portion of it.
Yeah, thanks, Cynthia. So because of the nature of the traffic in the corridor, there are only a few thousand vehicles a day that are passing through any specific location over the course of the day. The sample size from any one of these sources was obviously a concern. So we found that if you looked at one individual source, you weren't going to get as reliable results as if you combine, for example, Google with hair maps, with Waze, with other sources. And when we put all of them together, we're able to get information about incidents, information about events that were happening in the corridor, and the smoothing of the multiple ensemble of data sources was more accurate than just picking one individual source.
Okay. So was the system automated? Did it identify congestion on its own in real time? And did you use any AI applications to support the operation?
Yes, it was fully automated. It was extracting the data from the APIs in real time, aggregating it, determining what the baseline was based on the streetlight data, what it should be today based on the real-time weather conditions and other factors that were going into it, the day of the week, the time of the day. And when it noticed something that it was anomalous, it was also looking up and down the corridor. It's evaluating 100 different segments in both directions in real time. So when it sees that there's an anomaly, it looks and says, is it just happening here or is it happening everywhere? Is this something that's, is it something that's affected by weather? Is it something that's happening downstream that's affecting us up here? So I was able to take all that information in real time and identify where the congestion was, how severe it was, and how widespread it was. And when we saw something that was approaching even half of or even a quarter of that 20-minute threshold, we immediately sent an email to the project team so they could take corrective action.
Okay. So did you integrate Waze data into your dashboard?
We use Waze data just to understand the types of events. It was one of the sources that we used for speeds as well. And it was actually not as accurate as some of the other sources, but we did use that to identify, for example, where incidents were occurring. So when we see something that's anomalous, and if we see that there's a tag that's already been put into Waze that shows that, then we put that into the data logs. And one of the challenges with this project, or one of the goals, was to have concrete documentation so that if somebody goes to that corridor and they call in and they say that they experienced a certain level of delay 3 days ago or 2 weeks ago, we have a transparent record of what we observed at that time and what we attributed that delay to, so that we're not going back and changing notes, for example.
Okay. And how did you validate the accuracy of the system?
You want to talk about that, Cynthia?
Well, I would just say that in validating the accuracy of the system, it's really more about the heavy lift on the front end of aggregating lots of different data from different sources, like Sumit said, an ensemble of data. So we had a very strong background historical benchmark of the amount of traffic that we see up and down the corridor and through every one of these location points over time. And so we fully understood what we should be seeing. And once construction began, we understood what we would anticipate to see. And the real-time data just confirmed what was going on in real time for purposes of monitoring, and then the ability of the dashboard to provide the insights on what was happening up and down that corridor, and our ability to notify the project team where we were seeing congestion that was approaching the overall level mark of not to exceed, and then they would take corrective action in the field if it was necessary.
Yeah. I'll just add to that we had dozens of runs in the corridor. Whenever we had reports that there was an incident or there was something that was anomalous in the corridor, we had somebody actually try to drive that if there was somebody in the area, so that we could have that accurate data point. We didn't just want free-flowing traffic that we're calibrating to. We wanted to have all kinds of conditions. We wanted to have adverse weather conditions. So we had a wide cross-sample of conditions to calibrate against, and then we developed a predictive model that compared the actual field run data to our ensemble of online data sources.
Okay. And what methods were used for data collection?
It was primarily travel time runs. We were using smartphone-based location recorders that recorded the location every second. And we had a system set up where we could get that data in real time, but we also had the historical database. And then from that, we converted all of those travel time runs into segment speeds and used that to compare to the data that we were getting from the other sources.
And that is it for the Q&A session. So thank you, Patrick, Samit and Cynthia for all your insights. It was great having you, and that closes the session.
Thank you.
Thank you for having us.